Okay, so this is another optional part of the course in which I'd like to actually prove the formulas for the Laplace transform of the step function and the delta function. The first one at least is a simple exercise, but the second one for the delta function, the formula for the Laplace transform is not that obvious where it comes from, although the two formulas are similar. So if you're interested in what's behind them, I think it's useful to look at the proof of the formulas, because although, again, the Laplace of step t minus a and delta t minus a are very similar, right? I mean, we're going to write it down soon, but the Laplace of the delta function is just e to the minus as, whereas for the step function you have an extra 1 over s. So the formulas are similar, but the reason behind them, it's completely different. So for the step function, it's a very simple integral, calculus 2 integral, an improper integral. So it's nothing actually mysterious behind it. So let's remember how the step function is defined. For a given time point a, the function is equal to 1 if t is greater than a, and it's 0 up until t equals a. So remember the analogy with the switch, right? So the function does nothing up until time equals a, and then it returns 1. So when you actually try to compute the Laplace transform of this, so the Laplace of step t minus a by the definition, which is the integral from 0 to infinity, step function e to the minus as dt, I'm sorry, e to the minus st dt. So just the definition of the Laplace transform. Although the integral is from 0 to infinity, it's really from a to infinity, right? Because up until the point t equals a, the function is equal to 0. So you can break this integral into two pieces, from 0 to a, when the integral is 0, and then from a to infinity. So this is really equal to the integral from a to infinity, and the step function is equal to 1 on that portion of the domain, e to the minus st dt. So then what's the antiderivative of e to the minus st? Well, that's e to the minus st over minus s, because remember s is a constant at this point, and then you plug in a and infinity. I mean infinity, take the limit at infinity and then plug in a. So this will be the limit as t goes to infinity of e to the minus st over minus s minus plug in a for t, and you get e to the minus as over minus s. Of course, this goes to 0 if s is positive, as we normally assume, right? Everything we need to assume for that limit to exist. And then, of course, with the minus minus becomes plus, and this becomes a to the minus as over s. So this is where the formula for the Laplace of t minus a comes from. Okay, so here comes now the fun part, so to speak. Because remember what we told before, the delta function is not really a function in the traditional sense. So then, if it's not a function in the traditional sense, what do we mean by the Laplace of it, right? I mean, we used in this chapter that the Laplace of the delta t minus a is e to the minus as, but how is this obtained? Since we mentioned before that delta function is not really, it's a more like a generalized concept of a function, right? So where does that come from, this formula? Well, let's remember how the delta function is constructed, right? I mean, it's a limiting process basically. So you define basically a function that depends on a time interval length h. So let's call that function fh of t. Okay, so you start with a function that over an interval of length h, the integral of it returns 1, and then it's 0 elsewhere. Because then we're going to let this h go to 0 while maintaining that integral to be 1 at all time. So basically fh of t, and we wrote this before, if you remember, that's 1 over h if t is between a and a plus h, and it's 0 elsewhere. So remember that shrinking rectangle that whose height jumped up, right? I mean, to construct the delta function. So the graph of fh of t will look kind of like this, right? So nothing, I mean 0 for all time points except between a and a plus h. and between these points, between a and a plus h, the function will return 1 over h, so that the area of this rectangle is always equal to 1. And so this function basically, fh of t, converges, roughly speaking, to my delta function at t minus a as h goes to 0, but in a controlled manner, so to speak, right? I mean, it's not a traditional limit, it's a limiting process, so to speak, in which as h goes to 0, this integral is still 1, and then you'll obtain what we denoted by the delta function, which in terms of the rate, it returns 1 right at time a, and then it's 0 elsewhere. But again, the bottom line is that this is not a traditional function, so then how do I actually figure out what the Laplace of this is? Okay, so the Laplace of this is in fact also a limit of the Laplace of these functions which converge to this. So to figure out essentially what you call eventually Laplace of delta t minus a, right, the formula that you used, what one does is taking the Laplace of these limiting function fh of t, compute the Laplace of that, and then let h goes to 0 after that. So I should write basically here that essentially, let me put it differently here, essentially the Laplace of delta t minus a is understood as the limit as h goes to 0 of the Laplace of these limiting functions fh of t. So now I have to compute the Laplace of fh of t and then take the limit essentially. Now fh of t for a given h is just a piecewise defined function like any others. So similar to what we had in the previous case, right? The only difference is that at the end you take that limit as h goes to 0. So let's just do the Laplace of fh of t. So the Laplace of fh of t, again, according to the definition, is the integral from 0 to infinity of fh of t e to the minus st dt. But again, this function is 0 everywhere except between a and a plus h. So that means, let's continue here, that means this integral is really from a to a plus h of 1 over h, right? Because the function is equal to 1 over h between a and a plus h, e to the minus st dt. So h is a constant. The antiderivative of e to the minus st is e to the minus st over minus s. And then we're going to evaluate this function between a plus h and a for t, right? So we're going to plug in a plus h and a for t and take the difference. Okay, so let's do this carefully. When I plug in a plus h, I get e to the minus s quantity a plus h over minus s. And then when I plug in a for s, for t, sorry, that's, and I forgot the h here, right? So the denominator is minus hs. Okay, so minus 1 over hs, e to the minus s times s plus h, minus, on the top now is e to the minus as, because I plug in a for t, divided by minus hs. Okay, so let's see what we have. Let's combine this. We have the same denominator. So the Laplace of fh of t as a fraction is e to the minus s quantity a plus h minus e to the minus as over minus hs. Okay, so now we have to take the limit as h goes to 0, as I said before here. No, as I should have said. Well, no, yeah, as I said here, this is the step right here. So once we compute the Laplace, take the limit as h goes to 0. So let's take the limit as h goes to 0 of that fraction and focus on h, because now this is the variable at this point, right? I mean, we take the limit as h goes to 0 and treat everything else as a constant. And remember, we had something called the L'Hopital rule in calculus 1. If you look carefully, this is a 0 over 0 type limit. If h goes to 0 on the top, the difference between this is 0. H goes to 0 on the bottom, that's 0 over 0. So we could apply the L'Hopital rule, and via this rule, this is equal to the limit as h goes to 0 of the derivative with respect to h on the top and on the bottom. So again, focus carefully here. We're going to differentiate the numerator in terms of h. That means this part goes away completely because there's no h. And now we're going to differentiate this exponential with the chain rule. So the derivative with respect to h of e to the minus s times s plus h is the same exponential times the derivative with respect to h on the exponent, and that's just minus s. Oops, I always go out of range on the right hand side. So let me put it closer to the, so this is times minus s. Okay, so I hope that's clear. S is a constant. You differentiate this with respect to h, so it's minus s times the derivative of a plus h with respect to h. So that's 0 plus 1, and that's why you end up with minus s when you complete the chain rule. The derivative with respect to h on the bottom, it's minus 1 times s. H prime is 1. So notice that minus s cancels with minus s, and now as h goes to 0, all you're left with is e to the minus as. Okay, so in that sense, you arrive to the conclusion that the Laplace of delta t minus a is e to the minus as. So again, it's one of the most elegant things and interesting things in the theory of differential equations via Laplace transforms, because you basically have a generalized concept of a function to start with. So you know, it's not obvious how you actually how you deal with that function in concrete examples, let alone how you actually solve a differential equation with it. But the limiting process applied to not to the function itself, but to the Laplace of that function, happens to give you just a very nice traditional function, which happens to be an exponential. Similar formulas, but again, different reason how you arrive to them. So I hope that helps with understanding this part. And that's it for this addendum.